Welcome to ECE CS 552, lecture on integer multipliers. Earlier in the semester we covered number representations. We looked briefly at addition and subtraction, even with a carry look-ahead adder, and logical operations and so on, and dealt with the concept of overflow. In this lecture we'll be building on that to add additional arithmetic operations. We'll be looking at multiplication. We'll be looking at a specific algorithm called Booth's algorithm that is an optimization of integer multiplication. But before we get there, we'll just talk about basic concepts. None of this material is critical for the project since you're not expected to implement a multiplier in your processor design. Multiplication is really a flashback to third grade where you learned how to do multiplication. In implementing a multiplier, you have a multiplier, a multiplicand, you have a series of partial products that get generated as you multiply each of the individual digits of the multiplicand against the multiplier. And then you have to add all of those up together to create the final sum. So what happens here is the first bit is a 1. So our first partial product is an exact copy of the number being multiplied. As is the last one, however, it's shifted over just like we remember. But the middle two are all 0 because we're multiplying against a 0 in those cases. So that's essentially the algorithm. It's exactly the same algorithm as we use for decimal arithmetic, but it's of course much simpler because the multiplication tables are very small. We simply have to remember that multiplying by 0 gives us 0, and multiplying by 1 gives us what we already started with. So to generate the individual terms in the partial products, we really only just need a single AND gate. One of the things that comes up when you implement multipliers in a digital computer with a finite number of bits is you have to realize that the results are going to be up to twice as wide in terms of the number of bits required to express them as the inputs. So when you multiply two 32-bit numbers, you actually can get a 64-bit result as the product. This again is the same principle that we see in decimal arithmetic, where if you multiply two single-digit numbers, you could get up to a 2-digit result product and so on. We can implement this visually laid out structure directly in hardware in what's called an array multiplier. The array multiplier essentially uses AND gates to generate each of the bits in the partial product array, and then has a series of full adders that are connected in a Wallace tree-like structure to add all the bits up at each bit position to generate the final sum. This slide illustrates a 16-bit example of such an array multiplier. Each of the boxes that are shown in this diagram is a carry save adder. At the top, we only need half adders because we only have 2 inputs coming in. At the bottom right corner, we also can get away with a half adder. Elsewhere, we have these full adders that take 3 bits and reduce them to 2. We propagate the carried values diagonally so that eventually we end up computing the final, in this case, 32-bit product. It's conceptually a fairly straightforward structure to build. The hardware, however, is fairly expensive, requires quite a bit of area, quite a few gates, and quite a lot of wiring. It isn't easily justified because integer multiply operations are actually relatively rare in sort of normal programs. The most common place where you need integer multiply is when you're traversing array-based data structures to compute an index into an array. However, in that case, you can actually replace those multiplication operations with shifts and adds, which is trivial if all of your array elements are powers of 2 in size, but even when they're not powers of 2, you can do sequences of shifts and adds that are still going to be relatively efficient in terms of the number of instructions required, and of course will work on your existing data path that only supports addition and subtraction and shifting. It's really only when you get into application spaces like cryptography, for example, or signal processing kinds of applications where multiplication becomes important. And in those, if those kinds of applications are important for the product you're designing or the processor you're designing, then you'll want to add support for integer multiply. One way to avoid the expense of a hardwired array multiplier like the one shown on the previous slide is to do multi-cycle multipliers. So the idea here is reduce the cost of the data path significantly, but pay for it in terms of performance. So instead of a single cycle combinational multiplier that's very hardware intensive, we instead take multiple cycles to compute each product by iterating through the bits of the multiplier and then conditionally adding shifted multiplicand values to compute the final product. This slide illustrates with a block diagram how this might work. What we basically need is an arithmetic logic unit that allows us to conditionally add the multiplicand value to a product that's accumulating cycle by cycle, and every time we perform that conditional add, we base the condition on the corresponding bit of the multiplier, and then in the next step we simply shift the multiplier to the right, shift the multiplicand to the left, and repeat until we've performed this operation for every bit. In the case of a 32-bit multiplier that generates a 64-bit result, we would repeat this 32 times. So again, what happens here is we take the multiplicand, we load it into the multiplicand register, we take the multiplier, load it into the multiplier register, and then we have a control logic that essentially iterates through and for each of the partial products that are now just shifted copies of the multiplicand, it either adds them or doesn't add them depending on the value of the corresponding multiplier bit. This chart shows a flowchart that illustrates the decision making that the control logic would have to make to implement this multi-cycle multiplier. Again, we initially load those two values into the corresponding registers. Then for every bit position, we check to see if the multiplier has a 1 or a 0 at that bit position. If so, we do the addition. Then we shift the multiplicand and the multiplier, and then we check to see if we're done. If we're not done, we repeat 32 times. Finally, we're done, and we stop. There's a few improvements that we can consider to make this multiplier a bit more efficient. The first one is a big one. We don't really need a 64-bit adder to implement this process because at any particular point in time, we are actually not doing anything with the low order bits. The least significant bit is computed in the first step and is never changes after that. The second least significant bit is computed in the second iteration and is never changed after that. And so what we can actually do is we can use a 32-bit adder that just slides over the product at every step of multiplication, and there's really absolutely no need to pay for the hardware cost of a full 64-bit adder. It's also the case that we don't really need a separate multiplier register, so we can save a little bit on the flip-flop count that's required for this block because the low order bits of the product are initially unused, so we can simply just place the multiplier there, and as we shift product bits in, we simultaneously shift the multiplier bits out. Once we're all done, all the multiplier bits are out, all the product bits are in, and the final result is there. You can illustrate that simplified design on this slide. Again, we have a multiplicand that gets loaded into the multiplicand register. We have a multiplier that gets loaded into the bottom half of the product register, and then we simply iterate just like we did before and conditionally keep adding the multiplicand value to the shifted product. The flowchart is very similar, but as you can see, a bit simpler for this optimized multiplier. You can walk through this on your own. It's clear that the structure we showed before is operational or works for unsigned numbers. Let's talk a little bit about what happens if our numbers are signed. The first thing we want to think about is the expected outcome. So basically, if we're multiplying two numbers together, if one or the other is negative, then the product will be negative. But if they're both negative or both positive, we would expect a positive result. So what we can essentially express that using the XOR logic function as the sign of the product is going to be the exclusive OR of the sign of A and sign of B. So in order to do sign multiplication, one way we can approach this is we can convert the multiplier and the multiplicand to positive numbers and then multiply those numbers together and then compute the sign using this XOR logic. that's one way to do it, but as it turns out, it's actually much easier, again, kind of to do the magic of the 2's complement representation. All we really have to do is correctly perform sign extension on all of the shifts that we apply in the previous design, and the right answer simply falls out. An additional optimization that many multi-cycle encoders will employ is something called Booth's encoding. Booth's encoding is conceptually similar to a trick that some of you may have learned in grade school, where if you're multiplying by a number that's just a little bit less than a power of 10, so let's say you're multiplying by 9, instead of actually doing the multiply by 9, you simply multiply by 10, which just means shifting, and then you subtract once. So for example, if you're trying to multiply this 6-digit number 1, 2, 3, 4, 5, 4 by 9, you could generate all the partial products and add them all together, or instead you could simply multiply by 10, which means you just append a 0 to the original number, and then you subtract the original number from that shifted result. And what you end up doing is a shift which is inexpensive to do in hardware and just a single subtraction. So you save yourself quite a bit of work, quite a few steps in the process. So Booth's algorithm is a technique that allows us to apply very much the same principle, but with binary numbers, because in binary numbers we don't have 9s and 10s, we just have a 1 and a 0. So it's actually quite a bit less complex. So let's see how it works. The basic algorithm for Booth's encoding is to essentially search for runs of 1 bits in the multiplier. So whenever there are 1 bits, we're going to do something a little bit different from what we would normally do. Of course, whenever there are 0 bits, we simply don't do anything, because that's obviously the case. We don't have to even generate the partial products in that case, because we know they'll have the value 0. So an example might be the number 6 in binary. 0110 has a run of 2 1 bits in the middle. So if we're multiplying by 6, we can convert that into an equivalent multiplication by 8, which is a power of 2, which can be converted to just a simple shift, and then subtracting twice, since we know from our algebra lessons that 6 times m is equivalent to 8 minus 2 times m, which is equivalent to 8m minus 2m. So here we now have one subtraction of 2 quantities that can be derived simply by shifting. First, to get 8m, we shift by 3. To get 2m, we shift once, and then we subtract one from the other, and we have our result. So to generalize this algorithm for any number of bits, we basically are going to iterate from right to left, or from the least significant bit to the most significant bit. And every time we encounter the first 1, we're going to do a subtraction. And then when we've gone past the last 1 in that run, we're simply going to do an addition of the multiplicand to that product. And that's going to basically now effectively do exactly what we did in the example above. And then as long as we're in the middle of that run of 1 bits in the multiplier, we're just going to do nothing. And the same is true also for runs of 0 bits. Let's dig a little bit deeper there to make sure we understand what's going on there. So we've expressed Booth's algorithm a little bit more formally in this table form, and the rules are basically shown here. In order to implement Booth's algorithm, you have to inspect 2 bits of the multiplier at any point in time. You're looking at the current bit corresponding to the current bit position that you've shifted to in terms of which partial product are you actually considering. You consider the value of that bit as well as the bit to the right of it. And then depending on the values that those 2 bits take on, you can think of this table here as a truth table. You'll either perform a subtraction, do nothing, an addition, or again, do nothing. And the explanations are pretty clear here. Again, if the current bit is a 0 and the bit to the right is if the current bit is a 1 and the bit to the right of it is a 0, then you're beginning a run of 1s. So like we said before, we'll do the subtraction. If both bits are 1, then we're in the middle of a run, so we do nothing. And now if the current bit is a 0 and the previous bit was a 1, then we know that we've reached the end of a run, so we have to do an addition at that bit position. And again, finally, if both bits are 0, we're in the middle of a run of zeros, and so we're not going to do anything there either. The other way to think about Booth's encoding is just to think of it as a new way to encode numbers. So normally in binary numbers, we use positional weighting as 2 to the power n. With Booth encoding, each bit position effectively has a sign bit. So what that allows us to then do is to then look at that sign bit in the booth encoded form and decide whether we need to add or subtract for that particular bit position. Now, if you simply do boost encoding the way we've been talking about it so far, one bit at a time, you're not really going to save anything over the baseline multiplier that we already looked at, because you're still sequentially stepping through one bit at a time. The real power of boost encoding is that it can be generalized to multiple bits. So you can actually consider, for example, 2 bits at a time, or even 3 or 4 bits, depending on how much hardware complexity you want to handle. And it's a little bit confusing to understand how boost encoding works with multiple bits, so we'll go through that with a much more detailed example. So the basic idea behind a 2-bit per cycle booth multiplier is to now consider every pair of bits in the multiplier at a time. And again, you're going to look at those 2 bits as well as the previous bit from the preceding pair of 2 bits. And you're going to look at the booths encoded values for each of those pairs of bits. And if the booths encoding tells you it's a -2 case, then what that means is you're going to shift the multiplicand left by 1, because shifting left by 1 is equivalent to multiplying by 2. So that's how we get the magnitude of 2 effectively into our result. And then we're going to do a subtraction again because it's a -2. If the booths encoding is a -1, we'll simply subtract. If the booths encoding is 0, we do nothing. If the booths encoding is 1, we add, and if booths encoding is 2, then we again shift left by 1 to double it, and then perform the addition. So why does this work? How does this work? This table illustrates essentially the rules that were laid out on the previous slide, but supports their correctness by showing how essentially by following these rules, where you're considering 2 bits at a time, you're basically going to get the same effect as you would have had you applied the 1-bit Booth's algorithm to first the 2 bits on the right and then the 2 bits on the left. So the 2 bits on the right are underlined in green, the 2 bits on the left are underlined in red, and similarly the arithmetic that's shown in the explanation field of this table uses that same color coding to illustrate that in fact we end up with effectively the same result as what we get by simply examining the booths in 2-bit booths encoding rules. So let's just walk through the first row. I think the others I'll leave for you as an exercise if you're not convinced. But the basic idea here is if we were doing 1-bit booth encoding for that first row, 0, 0 for the green bits would imply +0. Similarly, 0, 0 for the underlined in red bits would imply +0. So mathematically, what we did then was in the previous bit position in green, we added a 0, and in the current bit position where the value is essentially double now, we also did a +0, and so the net was a +0. So we ended up doing exactly the same thing with 2-bit per cycle boost encoding as we would have had we gone 1 bit at a time with boost encoding. So numerically or mathematically, we get the same result. The main advantage again is once we've inspected these 2 bits, we can shift them out of the multiplier and inspect the next 2 bits rather than having to step through each bit position individually. And again, the idea here is not necessarily that you get a huge gain from going to a 2 bits per cycle Booth's algorithm, but you do get a significant gain, and you can extend this principle further to 3 bits per cycle or 4 bits per cycle. And now you start getting into the realm of designs that are implemented in real machines today. Let's come back to the issue of sign numbers or negative numbers. Again, it was pretty clear from the earlier examples that Booth works for positive numbers, but what about negative numbers? So let's look at a couple of examples here. What if we have a negative multiplicand? Like in this case, we have minus 6 times 6. If we essentially take that negative multiplicand and sign extend it to the full width. In this case, we're implementing an 8-bit example. We see that here, and then we follow the Booth's encoding steps for each of the 4 bits of the multiplier. We can express the multiplier in what's called the Booth's encoding format as shown on the slide here as reading from right to left, 0, minus, 0, plus. And again, the semantics of those zeros, minuses, and pluses are clear. At each of those bit positions, we'll simply either do nothing, or we'll subtract once, or we'll add once. So that's what we see happening here at each of the time steps. First, we're multiplying by 0, so our product is all 0. Then we shift the multiplicand by 1 to the left. And now we're subtracting. So in fact, the subtraction is going to give us the value circled on the right here. That's just the 2's complement of the value on the left. And then we will follow through on the next couple of steps. The next one, again, we add 0. And then the final step, we're going to add 1. And if we actually do the arithmetic for the second and fourth rows and add them together, we get the result shown on the bottom, which if you do your binary to decimal conversion, you'll see that that corresponds to the number minus 36. So engineering proof, we know that it works because we tried it with one example. Let's look at another example just so we can build up a little bit more confidence than we got from that single example. In this case, we'll have both a negative multiplicand as well as a negative multiplier. So once again, we take the multiplicand, sign extend it, and start with it, and then we take the multiplier and express it in Booth's encoding, following the rules that we introduced a few slides back. So in this case, we have a 0, minus, 0, 0 Booth's encoding, which we translate into the table now and perform the corresponding arithmetic operations, again shifting the multiplicand at every time step. And we get a final sum that if we do the math, we see that it, again, works out. We get the decimal value 12, which in fact is the product of minus 6 and minus 2. Summarizing this lecture, we looked at integer multiplication. First, we looked at a combinational solution that is fairly hardware intensive. Then we looked at simple multi-cycle implementations. And then we talked about Booth's algorithm as a way of accelerating the multi-cycle implementation from 1 bit per cycle to 2 bits per cycle.